Okay, looks like everybody's done. Let's hand in and let's get started with the lecture. So we had arrived at the point where in the process the steel chemistry is set, the temperature is set, the melt is homogeneous in terms of temperature and composition. So you're basically coming out of the secondary, very important secondary metallurgy, and your ladle is now ready to deliver the steel to the casting. Most of the casting nowadays is by continuous casting. So you produce a continuous and endless strip or amount of material, yes, continuously. The big advantages to working this way is in terms of cleanliness of the steel and general properties in terms of segregation. So compositional and microstructural homogeneity of the material is much better in case of continuous casting. You still do a lot of ingot casting, but those are usually in the area of used in the area of forgings, to make forgings. So it's not a very large amount of the production of steel production that goes into ingot casting. So we'll focus on continuous casting because 95 or more percent of the steels are actually made by continuous casting. So this is a schematic of what we call a slab caster. So you have a rectangular section, yes, and you can see where we start up there in the ladle. The ladle has an opening at the bottom, and it's poured into a tundish. Yeah? And the role of the tundish is basically to distribute the liquid steel in the caster. And the caster itself is a water-cooled, oscillating copper mold, and it's a bottomless mold. It has no bottom. Yeah? And that's what you pour. Yeah? We'll see what happens, but the material partially solidifies. Yes, yes, and you can and it's basically being pulled out of the caster by the oscillating movement of the caster. So when the caster goes down, the material moves down. Yes. The skin of what you just poured is solidified. So when the caster goes up, yes, it's retained by these rolls, yes, yes, and so slowly the material advances out of this mold. Yeah. We then have, in general, a bending zone. Yeah? So you cast vertically, and your material comes out horizontally, so you're going to have to do some change of direction here. So that's done in the bending rolls, and you have support rolls and bending rolls in this in this section. And in between the rolls, you will need to cool the material. Yeah, you'll need to cool it because it's not solidified; it's partially solidified. So the cooling is with water sprays between the rolls. Of course, you will lose heat to thermal radiation, roll contact, cooling, etc. And then at the end, you do the cutting of the this endless strip of material with torch cutting. And then what you get out is then called a slab. Let's have a look at some different types of casters. Yes. Nowadays, the types that you see most are called curved casters. Yes, but there are other casters, which the one is you have vertical casters. Yes, there you cast the material and you solidify it. Yes, in the vertical direction, and then you have special construction here that will flip it horizontally. You can have casters with a very long straight segment, yes, and then a bending. And these casters, the slab is bent in once it's solidified. And you have similar casters with a shorter vertical section. They will have the bending, the solidification will happen during bending. So, and there are different sizes. They're more compact, yes. But in the curved casters, you always have solidification during bending. So, why are people interested? Why did you decide? How do you decide which one to get? Obviously, there is a matter of cost. Vertical casters are expensive, obviously, because they're much taller. Yes. However, there are some advantages to the use of these casters, because there's no bending and unbending. There's no bending and unbending of the material, right? So when you bend the material here, it basically means that you bend it and then you have to unbend it, right? So there's deformation of the slab. Yes. So you're not going to have this type of stresses. Yeah. And then the metallurgical center, what we call the metallurgical center, that's where the solidification ends. Yes, is well defined. It's in the center of the cast material. Yeah? In the when you have a curved caster, the metallurgical center and the geometrical center of your slab or your billet or your bloom, they don't match. So it's off center, and you have, of course, bending stresses. So, in general, you will see that for higher-end products, where stresses, etc., are important, yes, surface quality, homogeneity, etc., you will see these kind of vertical casters. But in general, most of the time, you see basically a curved caster, yes. That operates on 2 floors, about 10 to 12 meters high. And this is a typical view here. This is the view of the casting hall. So you see here on one floor you have the casting floor. You have the ladle here, ladle here, ladle here. You notice they're mounted on a turret, so you can continuously pour material. So when this ladle is empty, you put this ladle in position, yes? And of course there is liquid metal in the tun dish, yes? So you can continue pouring while you are replacing the ladles, yes? And so the material, you don't see here the curves, but you see here the slab coming out. And if we look a little bit closer, this is the ladle. This is a tun dish, yes? which is basically like a reservoir for the metal and a distributor of the liquid metal. And here, this plate here, plate-like thing, is the oscillating mold. All right, let's look at more detail at first of all this tundish. Yes, tundish. So the tundish is where the liquid metal goes into first. It doesn't go right into the oscillating mold, right? So it's an intermediate container, and it's also a container that distributes the liquid. So why do we need this intermediate container? Because we like to cast continuously. So when the ladle is empty, yes, you need to remove it, change to another ladle. So there needs to be intermediate reservoir of liquid steel. So it has a special construction inside because you want to avoid turbulence. Yes, you want to have a very stable flow of metal, so you avoid turbulence. You can still use the opportunity to remove non-metallic inclusions because you need to protect the surface of the metal. It has a large surface of metal that's exposed to air, right? You need to protect that. So there will be some slag used here. Okay, and then you pour through these nozzle openings here. Now, usually the schematic here shows 4 different types. Yes, so usually there's one type. Yes, so but here the schematic show one type, what's called a metering nozzle, which is basically a hole. Yes, in the bottom of the tundish. Then you have what's more common are nozzles which give you the opportunity to open and close the flow of the steel. So here you have a sliding gate, or you have stoppers. Stoppers which will prevent the metal from flowing. So, then what is also important, the metal flows in these 3 last systems in a tube, which we call submerged entry nozzles. Yes, submerged entry nozzle. The word submerged refers to the fact that this tube is into the liquid metal in the mold. It's under the surface. Now, you have metal flowing through this system. You want to avoid oxidation. You want to avoid pickup of nitrogen. Yes. You want to avoid resulfurization. Yes. So we use shrouds. Shroud is basically you flow argon gas around all the critical openings, yes, in this system. For instance, here where the ladle is connecting to the tundish, where the tundish is connected to the casting. Yeah? So you have these very important flow of argon that will prevent pickup of nitrogen, oxygen, hydrogen, etc. Okay, that's the most important thing. So now the next thing is to look into the casting. The caster itself. The caster is basically an open mold, so a bottomless mold. So this is here the edge of this mold. It's copper, yes, and it's cooled. It's water cooled. So there's water flowing through it. And this tube here is the entry nozzle. It's submerged entry nozzle, and the metal flows through it and comes out through sides, holes made on the sides of this tube. Yeah? So it flows to the left here, to the left. Okay. Again, this the metal, yes, needs to be protected against reoxidation, yes, and we have what's called flux on it, or casting powder, yes. So this is a very special type of powder, yes, that will protect the material, the steel, from oxidizing, from picking up hydrogen or nitrogen, and it will also act as a lubricant, yes, so that it can slide against the mold. You have to imagine that when the steel touches the mold, it solidifies, yes, so it shrinks, right, and you slide it along the wall, and there is a liquid flux, yeah, which is formed at the surface of the steel. So, and you form a skin, yes, skin on the slab at the surface of the metal, yes, which solidifies gradually. But by the time you leave the mold, yes, this the steel is by no means fully solidified. There's still a lot of liquid zinc inside, yes, liquid steel inside, excuse me, and so in between the support rolls, yes, and the bending rolls, the ferrostatic pressure will deform the surface of the material, right? So you'll have some bulging, yeah. Okay, so in between, that's why in between there's a lot of cooling to accelerate the cooling here. Okay. Okay. So interesting. So this casting powder, yes, in order to make these fluxes is very rich in sodium oxides and fluorine compounds, yes, and so very often you may encounter in practice problems, surface problems in a product, and one of the ways in which you can recognize that an inclusion or a surface defect is related to the casting, yes, is by identification of the composition of the of these inclusions, yes, and this is the only place in the process, yes, where you use this type of slag compositions, yes. So high sodium and high fluorine contents. Yeah? So if you ever come across surface problems and you find high amounts of sodium, don't think it's sodium chloride, yes, or a corrosion problem. It may be a casting crack, casting related cracks. And of course, as we'll see, the risk of making surface defects is very high. You can imagine this is steel so the inside is 1500. It has to be higher than the melting temperature, right? So we're talking, depending on the grades, etc., 1500 to 1600 degrees, yes. In terms of casting, yeah. The strength of this high temperature film is very low, yes. So we're talking about less than 50 megapascal of strength here, okay. So the risk that you're going to produce surface defects is very high. Very often when you visit steel plant, you know it all looks like very powerful big machines, etc. But the steel itself and the heavy machinery that's all because it's very heavy, yes? But the steel itself, in terms of strength, yeah, is actually very soft. You can easily damage the surface, right? And so it's very important to never to forget that, because very often surface defects that you create during hot deformation and casting will remain in the material till the very end, yes? This is an example here where you're looking at a strand caster. So instead of having one single slab, you get strands of blooms or billets coming out of the caster. So for instance here, you see the ladle, yes? Here is the tundish, and this is the casters. Yeah? So now we have 1, 2, 3, 4 separate casters. So this is the top of the mold. Yeah? So you see the mold entry. Now the caster is basically this billet. Yes. Okay. It's not a big slab. It's a billet. And you cast, there's one entry nozzle for each billet. Yeah? And if you look down this caster, yes, the caster actually looks much more complex than just a piece of water-cooled copper. Yes. So this here is what you see if you look on the side. What you have is this construction here that will be moving up and down. Yes, it's the entry mold. Then we have here an attachment which is called an EMS system. That's electromagnetic stirrer. Electromagnetic stirrer. Talk about this in a moment. And then already attached to the mold, yes, section is you have the exit cooling of the strand. So the strand comes out, goes through an electromagnetic stirrer, and then right into the strand cooling. Okay. Yeah. So very important here to remember is so critical things are you want to have a shroud here. Yes. The clogging I was mentioning on Monday. This is where it occurs, right? This is where it occurs in the submerged entry nozzle. Yes, and you can see here that, of course, if you have large deposits of solid on this tube inner, the flow, the amount of steel that comes out will be influenced, right? And so you'll have an unstable casting. Okay. Right. Then, okay. So first of all, about this clogging here. Remember what I said on Monday. We add calcium to modify our alumina inclusions. You form calcium aluminates. Yes, and these are liquid. Yes, and so if they're liquid, they won't stick to this wall, and they'll just flow out. If you've added too much calcium, yes, you can have problems with calcium sulfide. Yes, and then that can also give you clogging or abrasion, and then the abrasion is again in this tube. Yeah. Okay. When the liquid moves out, yes, it goes with high velocity sideways. Yes, like shown here. Okay. Okay. Right. Now, we don't like to do this. Yes, we don't like to have this kind of strong flows whenever you cast. Yeah, and that's one of the reasons why we add these electromagnetic stirrers, the EMS systems, yeah? To control, yes, what is left of liquid inside the material. Okay, and we will add these electromagnetic stirrers at different positions. First of all, let's have a look at what the functions are of these electromagnetic stirrers. Yes. Segregation, you can influence segregation. You can improve inclusion removal. You can decrease temperature loss or inhomogeneity. And minimize a very pronounced solidification microstructure. So these EMSs can be put at different places during the casting. When we put them up high, yes, in the caster, yes, like when we put an EMS, for instance, excuse me. Okay, like in this case, the effect of the EMS is to work as a brake, yeah, like a brake. What you do, let me get a pen here, so sure. Yeah. By having basically you have an inductor here, right? You just have it's basically an inductor, yes, a coil that you pull. Yeah, it will provide a force, electromagnetic force that goes in this direction, so that breaks the flow of the outgoing flow of the metal. Yes, okay. So you basically avoid very high velocities here. You can also put an EMS later. Yes, there it will mix the metal. It will keep the metal moving so that you don't have compositional gradients. Yeah? Let's have a look at that. Okay. So why is this important to minimize compositional gradients or to minimize microstructural feature? Well, if we have, you probably know this from undergraduate studies, is when the metal will solidify, like steel solidifies, you form, when the cooling rates are not too high, you form large crystals. Yes, large crystals which we call dendrites. Yes, dendrites. Yes, and during the solidification of these dendrites, we get partitioning. So certain elements will enrich in the solid, other elements will partition to the liquid. Yes, so we get two things. Yeah, we get dendritic microstructures, and we get compositional differences. Yes, the center here doesn't have the same composition as on the side. So, but by mixing the liquid, yeah, while it solidifies, we can minimize this. Right. This is actually a continuously cast microstructure. It's an example of a 439 stainless steel. Yes. So the microstructure that it doesn't go through transformations like regular carbon steels or austenitic stainless steel. So the microstructure you get in the slab is actually the high temperature structure. So you can see that close to the wall of the copper mold, you get very quick solidification. Yes, and so you get small grains. That's good, but inside, the cooling rates drop dramatically, and you get these dendritic microstructures. So that's why we will add these stirrers. So this is an example here. It's a billet, yes, a square billet, not a slab, a square billet. And this one is cast without an EMS, and you can see this patterning here, which are dendrites. Yes, there are large dendrites. If you have an EMS in the line, you can minimize the growth of these dendrites, and you can also see that the center line segregation is much lower. So you get your billet is more homogeneous. Okay. Okay. Now, a lot of this equipment and attachment to a line depends on your investments possibilities that you have, and on how worried you are about quality issues. Yes? So you have casters which have EMS everywhere, yes, and you have casters who have none, yes. So it's not always there as a rule. Depends pretty much from company to company. All right. So again, when you look at the casting, yes, it looks like there's nothing much to it to worry about it. It works very smoothly, nothing happening, right? But there are many issues that are of importance to steel products, yes, and in particular related to defects, which we generally call cracks, yes. And cracks is a very, surface cracks in casting. It's a big bag of many things, yes. So one of them, which is important for steel products, is the peritectic steels. Yeah? A peritectic steel is defined as a steel where when you solidify it, it goes to the peritectic reaction. Yeah? So this is the only time that I focus on another part of the iron-carbon diagram in this course, and that's at high temperatures. So at high temperatures, in your iron-carbon diagram, you have the peritectic reaction, yes, here. Okay? And if you have steel compositions, yes, less than 0.2% of carbon, and those are many steel compositions, yes, you will go through two contraction steps. There are two during solidification contraction steps. There's a first contraction, the reactions are shown here, yes, when the liquid, so you look here, yeah, oops, in this zone here. Yeah. So first, when you solidify, the liquid goes to liquid plus delta, yes. So there is a solidification here, a contraction, yeah, during solidification. And then there is a second contraction when you go through the peritectic reaction here at the peritectic, yeah? And that is the liquid becomes gamma, a mixture of gamma plus delta. And you can measure the thermal contraction, yes. If you do the casting in this zone here, yes. Depending on what temperature you look, right? You do the solidification here. So you see this big contraction, yes? And if you do the solidification at lower temperature, it becomes even bigger. Yeah? Okay. So what does that mean? You have a surface, yes? It contracts. The center doesn't contract, right? So you've got stresses. This is material at between 1400 and 1500 degrees C. I just told you the strength of this material is very, very low. So cracks can develop at the surface, yes, small cracks. So when people measure the occurrence of surface cracks, they always observe a very large maximum of surface cracks at 0.1 to 0.2% of carbon. Yeah? And what people also measure is, for instance, the depth of what we call oscillation marks. You remember that I said the casting unit moves up and down with a certain frequency. And so it moves up and down about some of the order of a centimeter, yes, up and down with certain frequency, yeah. And every time it goes up and down, yes, you will have stresses, yeah, because when it moves up, moving down, it's together with the slab. Moving up, you stress the slab, right? And this motion, yes, oscillating motion, leaves also surface marks, which we call oscillation marks, yes. And casters and steel makers in general don't like big oscillation marks, yes. But you can see that the depth of the oscillation marks, yes, are very large in the case of peritectic steels. Okay. Okay, so peritectic steels, very careful. So steels are sensitive to surface cracks because of their composition, yeah, and the way they solidify. You can get other cracks in developing in the material. You remember that when you cast a slab, yes, you also, in many of these equipments, you bend it, yes? So you actually put deformation on the material, okay? So what happens? Well, you can get cracks develop. This is an example here where it's really bad. I mean, a good example of a bad slab. What's the big cracks? Yes, in a slab. You're cooling the material, right? And we know that in our composition, we, for instance, added niobium or vanadium because we want to do some precipitation hardening. Yes. And so what these compounds do, they precipitate while we're cooling the slab and casting it. Yes. And because we're cooling very slowly, yeah, they tend to form precipitates at grain boundaries. Yes. And they weaken the grain boundary strength at these very high temperatures. Right. It's not a problem at room temperature because you control the distribution of these precipitates. But at high temperature, they form where they want and they're very coarse. Yes? So we observe a ductility gap. Yes? So if you measure the elongation of a material in conditions of continuous casting, very important. So very slow strains. Yes, at very high temperatures. Yes, and you measure the reduction of section, so the plastic deformation of the where you get the fracture. Yes, so if something is very plastic, the reduction before fracture is very large. Yes, 100%. Yeah, so at high temperature, that's what you measure. 1,000 degrees, you measure very high ductility. But if you go to in the range of 800 to 900 degrees, it just drops to 30%. So your material is like unbrittled, yes, due to these precipitates here. And then at lower temperature, the ductility comes back. But these kind of temperatures, the slab is exposed to. Yeah? For instance, at the surface. Yes. And so this can also give cracks. And if in really bad cases, yes, the cracking can even be inside the slab. Yeah, so hot cracking. Okay. Okay. So this is what comes out here. Again, the slab looks nice and straight. Don't forget it's been bent once and twice, bending, unbending, and then it may have cracks at the surface. Usually for slabs, you're looking at 20, 5 centimeters of thickness. Their length is about 10 meters, can be longer, 12 meters, but that's typical length. And the width depends on, for slab here, at the width of the caster, yes? And the width doesn't change very much, yes? So the caster, actually also, the dimension of the caster also defines the maximum width of, for instance, sheet products that you manufacture. So if you have caster that can only do 1.2 meters, you will not be able to provide material to customers that need 1.6 meters. Yeah? For instance, automotive construction needs, 1.6 very common, right? So the caster should be able to provide this material. So, right, and once the slab is made, it cools, it's marked, you remove burrs, and then you stack the material. Because this process is an endless process, yes, you basically have to produce the same thing all the time, right? So how do you make different compositions, right? So you want to have a low carbon steel, and other time you want to have a microalloyed steel, right? So how do you do this? Well, you have to make transition slabs, yes? You have to basically, if you want to make a change in steel chemistry, you will have to waste material. You'll have to cast slabs that go from the previous chemistry to the next chemistry, yes? And so you can, depending on how good you are, yes, and of course what product it is, you can have to scrap a few slabs or a few meters of materials, yeah? A few meters, that may mean quite a few tons of steel, okay? Yeah. So it's expensive, okay? So when, as a young researcher, you go to a steel plant, you cannot ask them to make something for you, right? Because it doesn't work that way, okay? They cannot make something for you in a steel plant just like this. Yeah? This needs to be organized, because normal production is all programmed. Yeah? Good. And that's also always why it's so challenging to introduce new products in big companies like this, because the plants are designed for continuous production. So there is not much space. There's no space to do experiments, yes, or very little. And so introduction of new products means a big organizational task group has to be organized to do this, yes. Right, so typical things here: exit temperatures, slab thicknesses, again, as I said, typically 25 centimeters, lengths 10 to 12 meters. And okay, so the width of the slab is, has big impact, because obviously, here, this is 1 meter. The equipment that comes next, the hot strip mill, has to be able to roll this material, right? So everything, the hot strip mill dimensioning has to be in agreement with the widths that is provided, and the final width requirements. Okay. There's one thing, just for your information, that is sometimes used. That's called the PIW. It's used in North America. It means pounds per inch of width of your slabs or your coils. Yes, and the reason why it's used is because it gives you an idea of your mill size, your caster size, yes, and what it basically is a very simple concept. Is when you have, take for instance, you have a slab here, yes, and the slab is turned into a strip here that's rolled, and then into a cold roll strip, yes, that's coiled, yes. The amount of material, yes, in terms of weight that you, so if you cut off here 1 millimeter of material from this slab, yes, or 1 millimeter from this intermediate product, or 1 millimeter from this coil, it all has the same weight, yes. So that gives you, it basically gives you an idea of the kind of productivity your mill can achieve. So it's basically specific coil weight. Yeah? It's the weight per inch of width, or per millimeter of width. So what is it? Is how do you calculate? Is the length times the thickness times 12 times the density. And you can, if you want to use metric PIW, so that's basically kilograms per millimeters, yes, of width. It's the American, the PIW divided by 50. So what typically modern production units are around 20 kilos per millimeter. So that's if you take a strip of coil, you cut it off, it gives you about 20 kilos per millimeter. So this is an example here, yeah. For instance, 1,000 pounds per inch width PIW coil, yes, you can recalculate this, that this is 21.5 kilos specific weight. Okay, so it gives you an idea of coil sizes, slab sizes that are routinely used in the steel production unit you're visiting, for instance. Okay, now it's always interesting to spend some time talking about nomenclature. Yes, so a caster will produce slabs and blooms and billets, and so what are these, and what's the difference? Well, and also what's important to realize, these products, slab, blooms, and billets, are also products that a steel plant will sell to customers. Yes. So we call these products. We give them following names. So, what the steel company produces are what we call semis, semi-finished products, and finished products. Yeah? So, for instance, what is a semi-finished product? Yes, the semi-finished products are slab, blooms, and billets. Yeah, so semi-finished means like half finished. Yes, it still needs processing. It's not a finished product. What is a finished product? Are the things we discussed previously. For instance, sections, bars, wire, rails, or flat products, plates, hot rolled strip, cold rolled strip. Yeah. Right. So slab, blooms, and billets. So what comes out of a continuous cast of a steel plant, basically, are semi-finished products, and they will be processed further in other companies. Yes. Yes. They can be processed inside the company that produced these cast products, or they can be sold to outside products. Yeah. So you can already see these two products where there's always a lot of confusion about what's the difference. Yes. Well, so a bloom kind of looks like this and a billet looks like this, right? Well, where do we make the difference? Right? Where does our definition between bloom and billet change? Well, in other words, what's the difference between a billet and a bloom? Well, anything that's larger than 7 by 7, yes, is called a bloom, yes? And when it's smaller than this 7 by 7 inch, yeah, that's about 17.5 millimeter, we call a billet. Yeah? That would be simple, yes? It's a simple definition, but billets and blooms come in different sizes, yes? They're not always square. They're not always square. They can be round, they can be rectangular, yes, depending on the application. So what we usually, alternatively, can see, so your bloom caster will produce blooms. That can be square, but they usually rectangular. They can be round, yes, and they can also have a shape. Yes, in this case, we don't call them blooms. We call them beam blanks. Yes, beam blanks, and they can be used to make. These beam blanks can be used to make beams, but also rails. Okay. Right, and typically. Again, at around 20 centimeters, yes, anything that's smaller than 20 centimeters, we call billets. Yes? And you have billet casters. They will produce square sections and round sections, which are typically less than 200 millimeters in dimensions. Yes. Diameter smaller than 22 centimeters for round sections. Yeah? And again, also, if you let blooms be rectangular, what's the difference between a slab and a bloom? Yes, because they're both rectangular. Well, a slab caster, of course, makes products that will be used to make flat product strip, yes. Their width is usually more than 60 centimeters, and the ratio of width to thickness is larger than 3. Okay, that's kind of a way to make the difference or choose your words well. Okay, so this is an example here, right, of blooms. Yeah? So blooms is what basically comes out of a bloom caster, yes, in a steel plant. So this one is 13 by 13, yes, and this one is 250 by 250. So hereabouts, yes, would be the difference between billet and blooms, yes? But nobody's going to be upset at you if you call them all billets, yes? And these are beam blanks, and here you see that you basically pour the steel in a shaped caster, yes? Okay. Okay, and this is what you get to see in plants that make this. So slab casters produce slabs. Your casters can have many parallel strips. For instance, this one here is a double strand slab caster. And so the width here is 1400, yes? And of course, the more strands you have, the more capacity you have. Yeah? So a double strand caster, which the casting speeds, by the way, it's kind of interesting to know what typical casting speeds are. About a meter per minute. Yes, so it's pretty slow. what are high casting speeds are 5, maybe 6, and what's the world record? Maybe 7 to 8. Yes, so for much thinner materials. This is 23 millimeters thick. Yes, yes. So if you have a thinner strip, yes, yes, and you can only go 5 times faster in casting, your production rates will be much slower. Yeah? So compact strip casting, which we will talk about later, have usually much lower production productivities. Okay, and this is these slabs being cut, the strips, these endless strips being cut. This is an image here where you have 3 strands, so 1 strand, 2 strands, 3 strands, and then round, you can see the section here, round billets. Let me see. Well, it's 230, so I guess we should call it round blooms, yes, according to my own definition. So you can see here the round, and again you produce them in parallel. Casting slightly higher with the billets and about 2 meters per minute. And here you see 4 strands, and you see that these billets are square. So that's basically the shape of the caster. All right. One of the important things people do after the slabs or the billets or the blooms are produced is have a look at the surface quality, because you have cracks, many types of cracks, longitudinal, transverse. You have segregation you can have center lines that are open. That means that inside the material there is actually a solidification porosity, yes, an open center line. You of course have oscillation marks due to the oscillating mold. You can have heat checks from scarfing. That may be a little bit mysterious. Sometimes the surface quality of a slab is not very good, and you will burn off these defects with a burner, yes, by hand or with a machine. Yeah, you basically melt the material. Yeah? You melt away the material. And that's called scarfing, slab scarfing. So there may be surface defects related to this scarfing, which we call heat checks. Scarfing curve is surface damage due to scarfing, handling damage, of course, and heat checks from ripping. Certain slabs will actually break in a brittle fashion. Yeah? And it's well known that, for instance, high silicon slabs are very sensitive to this problem. Some pictures here. Yes. Here you see these oscillation marks. These oscillation marks, you know they're oscillation marks because they're periodic. Yes. Here you see an edge crack. Yes. Here you have a center line crack. Yes. And of course, inclusions can always be a big problem. So that's a big headache, of course, these cracks. And in practice, they get a lot of attention, certainly if the cracks are major. And they can be major. Sometimes the cracks are not very visible. For instance, you can have a crack at the surface of a slab, yes? Yes, and that oxidation and removal of scale will round the sharp edges, yes, and deepen it. But when you start rolling these surface defects, they will tend to have to be closed by the rolling process, yes. And so you get things like rolled in oxides, yes, that are not really visible anymore, yes. You have to imagine these are not very huge cracks, right? The small surface cracks, yes. And you basically, the cracks and these oxides disappear under the surface, and then they will reappear when you, for instance, do a deep drawing operation. You'll get these really bad surface defects, okay? And you'll have to figure out, where they come from, and certainly if it's affecting a lot of the production. Okay, and these are other very serious cracks here that, again, will often not appear very clearly in the slab, but will give you major problems when you start rolling the material. So this is, for instance, a slab that was fractured during hot rolling, during the rough rolling stage. Okay. Okay, good. So when we reconvene on Tuesday, we'll be talking about the next step. What happens to the cast steel that we made? Yes, and we'll focus in the coming lecture on hot rolling, and we'll see how the material, yes, and we'll focus first on slab materials for strip production, how this material is reheated, yes, goes through roughing mill, yes, goes through a finishing mill, run-out table to cool it, yes, and then is being coiled, yes. In the process, the material gets thinner, yeah? So you go from about, say, 250 millimeters to an intermediate thickness of 20 to 30 millimeters. Yes. The material at this stage here is called a bar. Right. So as a steel student, you should definitely know that there are bars and that there are bars. There's bars where you enjoy your drink, and there's also the transfer bar. This is the transfer bar. This is a rough rolled slab. And this transfer bar, is then further reduced to 1.5 to 12 millimeters thickness, typically 5 to 6 millimeters before you call. So in the process, many things happen. The microstructure evolves, the temperature drops, we get phase transformations, etc. So we'll be talking about this on Tuesday. Start to talk about this. On Tuesday, we'll first focus on, because I don't know what your knowledge is about the rolling process. Yes? So we'll first introduce a few concepts about rolling process that you need to know if you want to understand what happens in a hot rolling mill. Okay, so thank you very much, and I'll see you Tuesday.